cloud. And then I am also going to share my screen, share the sound this time. I have a lot of, I have a lot of, I didn't open the PowerPoints, sorry. I have a lot in this chapter. Yeah, go ahead.
I have a question about the technology evaluation discussion. So we're supposed to put a reply in every other group that we weren't in?
Yes, correct.
Okay, all right.
Which I see some students are doing that now, because I don't know if you guys get the same, every time somebody replies to the message, and I get emails on those, just so I'll see somebody, you know, every like 15 or every half hour, I get this person replied, this person replied. I get blitzed with emails on these things as students are doing them. Let me go find this. Actually, I'm gonna take it out of the chapter. I should. Let me open it from here. All right, I should have this open already. Darn it. Okay. Get distracted. Chapter 14, my favorite, the last one. Not necessarily favorite in content, but favorite because the semester is almost over. Actually, this is a good chapter. The book used to have chapter 14 AI stuff used to be as part of another chapter, but with the evolution of AI, it has now become. Where's it? There we go. Sorry. But with the evolution of AI, the author a few years ago decided, this is important enough. We need to start. We need to make its own chapter. I don't think they've quite done it justice, and this is very high level kind of AI stuff. Because AI is expanding dramatically as we speak, and they'd have to come out with a book very soon to catch up with that. Couple administrative things. I am pretty sure I am going to get done with chapter 14. It may run a little long today, it may be a little longer, but it's a very short chapter. So I am going to do my best to get all the way done with 14. So there will be no class on Thursday. I will not be doing a session from my home on Thursday. And so I'll put an announcement saying that, specific, especially if I finish, which I fully expect to. Other things, the final exam is next week. The final for this class is on Thursday in here at 9 o'clock. So, which is kind of weird. They stagger them. I don't know if you're aware of that. They've always done that. If you have two different classes that are back to back, like I have this one at 9 and then the other one's at 10:30, they stagger them. So if a student has a class back to back, they don't have to try to study for both of them simultaneous. So that's why they do that staggering. They never have the back to back. So these are back to back classes. So yours will be on Thursday. My 10:30 is at 10:30 on Tuesday. If you want, I always make it available. If you would prefer to take it on Tuesday, works better in your schedule. You can come, but at the 10:30 time, it'll be 10:30 in here, on Tuesday. That makes sense? Is that pretty clear? Your choice. Just let me know. And, I may recognize you. Oh, wait, you're in the Tuesday, the 9 o'clock class. And because I have to open it up, I won't be available to you. So you have to make sure you let me know. All right, anything else? The last chapter, groups 5 and 6 need to submit their video by midnight tomorrow. So make sure if you're group 5 or 6, make sure you do that. I started watching a couple. I haven't really graded them all yet. So I'm going to probably do that. Since we have no class on Thursday, I'll probably do it Thursday. And then what I don't get done Thursday, I'll finish Friday. I will probably not post the grades until after the final, because I think as I mentioned, one of the things I like to do is give an evaluation, a group evaluation form to everybody. So you can tell me, if somebody in your group didn't do anything or very, very poor attendance or performance. And then it's a group grade. I give everybody the same grade, except for those kinds of things. I look to see if you met the timeline and, certain things, but other than that, it's a group grade. Make sense? All righty, let's get into chapter 14, artificial intelligence. Very interesting stuff now. It's become more and more interesting of lately. So I'm going to jump in, come over here, talk about, let me get my slides here going at the same time. All right, artificial intelligence, and here's the definition from the book. The theory and development of information systems able to perform tasks that normally require human intelligence. And so what it is basically, this has been around for a long time. I think I started hearing about, in the technology world, this thing called artificial intelligence, probably mid to late 80s, 1980, early 90s, certainly. So we've been talking about doing it, but because we haven't really established it, and I'm going to talk about what's enabled it. The next chart talks about what it is, or next chart or two talks about what it is and why that's been enabled. So I'm going to jump over here and talk about a couple different things. What this thing called the Turing test. Let me jump on that and show that real quick. Little short video.
At Target, try fast and free drive up.
Gotta have a Target ad first.
The Turing test, created by pioneering computer scientist Alan Turing, comes up a lot in sci-fi culture and discussions about intelligent robots. But what exactly is the Turing test, and what does it mean if a computer passes it? Alan Turing first described what we call the Turing test in a 1950 paper. Turing wanted to answer the question, can machines think? To get to the bottom of this, he devised a hypothetical test. Imagine a game with 3 players. One player, the interrogator, is isolated from the other 2 players, one of whom is human and one of whom is a computer. The interrogator's job is to try and figure out which is the human and which is the computer by asking questions of both. To make things harder, the computer is trying to make the interrogator guess wrongly. In other words, it's trying to be as indistinguishable from a human as possible. If, more often than not, the interrogator is unable to determine computer from human, then hey, maybe we're dealing with a thinking computer. Attempts to build computers that can fool humans have revealed some fascinating challenges. For instance, it's hard to make a computer that's good at telling jokes. The Turing test isn't a perfect test of robot intelligence. For example, it encourages trickery. One recent attempt involved a program pretending to be a young boy for whom English wasn't a first language, conveniently covering up any linguistic slips. The Turing test also doesn't account for non-human intelligence. Some of the smartest computers around today have no chance of pretending to be a person, but that doesn't make the advances in AI that they represent any less impressive. So just because a computer looks like it's passed the Turing test doesn't mean we have to bow down to our robot overlords just yet. But nevertheless, Turing's experiment gives us plenty to think about in terms of how we define intelligent behavior and what we would want from an intelligent robot. And after all, who doesn't like thinking about robots?
All right. That's fine. All right, so basically, the Turing test is a test to try to figure out, is artificial intelligence, can it fool a person that it thinks it? So it's, like they said, they have 3 things. They have a computer, a person answering the question, and then a person interrogating, asking questions. And then the person asking the questions is supposed to figure out, was that a computer that responded, or was that a human that responded? And if the person can't tell the difference between the computer responses and the person responding, then the computer is probably, is past the test. Very few things, and I believe it's still pretty much, it's pretty close. I don't think anything's passed. I haven't heard of anything passing the Turing test yet. So there still is the belief that, I need to go look at that with the latest developments in AI. There may be stuff that's actually fooling it now. But up till, I don't know, at least a year ago, I would say, there had not been anything that had passed the Turing test. All right, so there's two different kinds of things. Actually, I have tons of videos in this one, so I don't know if that's gonna make it easier or harder to get through this time.
It's a fact. In the new economy, average people are becoming millionaires faster and easier than ever before. But how do they do it? According to the news, the whole world's falling apart.
Only a million.
Hello and welcome back to The Daily Fort. Today we're talking about strong versus weak AI. So today's question of the day is, what is strong versus weak AI? So while strong and weak AI might sound like very objective technical terms, they're actually a little subjective. So a strong version of AI is one that has a mind and can think. It's conscious, it's self-aware, it mimics a human mind. While a weak AI appears to mimic the human mind, but is actually only acting like it's thinking and can generally only perform a specific task. So while we haven't created a truly pure, strong AI, there are many different artificially intelligent systems that are strong in one area and weak in a lot of other areas. For example, there's an artificially intelligent program called AlphaGo. And this artificial intelligence is amazing at the game Go. So you could say that it has strong artificial intelligence when it comes to Go because it mimics the human ability and sometimes surpasses the human ability to play this game. But this same software couldn't decide on a restaurant or write a novel, so it is not truly a strong AI. So this has been another edition of The Daily Fort. Comment any questions you have down below. All of my social media links are below as always. Like this video, subscribe to the channel, and slap.
Yeah, whatever, buddy. All right, so yeah, strong versus weak. Let me jump back over here. Strong versus weak. Strong being, it can do lots and lots. To be truly a strong AI kind of device, it has to be able to do several different things that the human person can do. And as they point out in here, most things may be strong in a specific area, like he showed in that game, which I've never played, but play that game. Go. I've never, before I saw this video, I didn't even know it existed. I have no idea what it is. But but there's other programs, chess games, any chess players that play against computers. Yeah, they're strong in playing chess, but probably can't do anything else from an AI perspective. So it's kind of along the same lines of the Turing test. There's really not a lot of things that are considered fully strong AI. They're more weak. They're good in a specific area, but they can't do other things. And weak AI tends to be stuff that can perform useful tasks and do helpful things, but they don't have that thinking ability quite as well developed as we do, as the brain can do. Although some days I wondered, I don't know if I can, I think weak AI is better than me. I don't know. Anyway, artificial. So now in the next chart, I'm going to talk a little bit about some of just compare stuff that we have. You've got to change it here too, don't talk, little capabilities, kind of comparing human intelligence or natural intelligence, as they're calling it, versus artificial intelligence. Some of the different things: preservation of knowledge. One of the things that over time, and especially the human natural thinking kind of thing, we can forget certain things over time. We forget certain levels of knowledge. Whereas once you program it into artificial intelligence, it's there, it stays there, it does not change. So that's one of the things that that is is a difference between the two. Some of the things: total cost of knowledge. Cost of knowledge. I skipped one there. I don't know. Can be kind of difficult. How do you put a value on, and how do you train somebody to be knowledgeable? Very hard, because some people just, and I'm a firm believer, we're not all given this. I refer to I'm an IT guy. We're not given all the same chips. The way I think, I'm a very logical, I'm math oriented kind of guy. Some people, certainly I have relatives in my family that couldn't solve a math problem to save their life. Hold a gun to their head and they're going to, oh my God, I'm going to die. But there's certain things they can do very creative. I am horribly not creative. If you hold a gun to my head and said, draw something or do something very creative, I'm going to die because I am not a creative person. And so that's why I think we are, those kinds of that intelligence within human beings is very different. So capturing that and is very difficult. We can't, the cost of obtaining that can be hard from a single individual kind of standpoint. Some of these other things, creativity, like it says, it's one of the options there. Can be very high because you may not have that. Whereas we can create AI systems to be creative, teach them certain things. And we're seeing that more and more with things like ChatGPT. You give them certain parameters. And I just saw something the other day. It says you put in certain parameters, create an animated figure based on 4 or 5 different things. It'll create an animal or something, and it'll create something very creative for you. So that is available. And so this is just kind of I'm not going to go over all these. This is kind of a shopping list, kind of comparing what artificial intelligence can do, how much it costs, and how difficult it is for one versus the other. Probably not a surprise. All right, next. So what has enabled us? What are the technologies or things that have made this available? Advancements in chip technology, why can we do this now? Like I said, and actually you know, I certainly was aware of in the eighties of when, you know, maybe early, mid-80s, I don't know, of artificial intelligence. I'd heard about it. I didn't really study it. I didn't know much about it, to be honest. I didn't start probably looking into it, it's around the early 2000s. But it's been around, and as I think the video said, this Turing guy created that Turing test. I think they say the late 50s. So it's been around 50, 70 years, 70, 75 years now. So it's been around a while. So the concept of having artificial intelligence has been around, but the development did not make it nearly as fast. We're just now getting to the point where things like, you know, this is the shopping list of why it's enabled now. Chip technology, you know, the making of the chips, the CPUs, the computer parts, the thinking parts of a computer weren't as advanced. They just couldn't do a lot of things. To do artificial intelligence, it takes a lot of processing power. You have to be able to do a lot of calculations and a lot of looking at different things very quickly. So we didn't have the chip technology until more recently to do that in the last 5 to 10 years. The next one, big data, which, as you recall, chapter 5. Now we have lots, because we have computers, we have lots and lots and lots of data. And in order to make smart decisions, that's one of the things our brain does. You know, believe it or not, one of the things we do fairly well is store and can comprehend and see a lot of different things. So our brains gather lots of data in our brain and we make decisions. Well, computers have a finite ability, but we can put more in there. We can put large masses of data into these things, and then we can use that. We can sort through it and find it. Not only do we have, you know, we have our own kind of stuff. We can look, you know, and, you know, on premise or whatever within our own computers. But now we also have this other stuff, this thing called the internet and cloud computing. So we can search within our own data structures, databases in our own big data kind of environment. But then we can also go out and search over the internet. We can search cloud. So what it does is get a wealth or more richness of information. We can get better solutions because of the vast amount of stuff out there. And then the last thing, improved algorithms. Algorithms are the processes or the steps that you go through to look at these things and do this. We've gotten smarter. We have a lot of smart people who study different things. We're going to talk a little, or show a video at least of some of the different things, neural networks and some of the different ways people have studied. We have smart people that have studied the way the brain works and try to emulate that or make the computer systems work in those same things and learn kind of information as well. All right, so moving on. All right, so now we're going to go and look at a few of these. I think this is a lead-in chart. Yes, it is. So these are what we're going to look at. There's 3 different types that we're going to talk about. There's actually subsets of these and there's a variety or 2. But for the sake of this class, these are the only 3 we're going to look at: expert systems, machine learning, and then this thing called deep learning. So let me jump over that since it's just a lead-in chart. All right, so what are these things called expert systems? Expert systems are, are experts from a domain or the source of the system. Basically what it says, you know, if you've been in the workplace or you've been in school or whatever, there are certain people, they seem to be expert or they're smarter. They've known a lot about something. And so that's what we're defining as an expert. Somebody who is, you know, knows a lot about a certain area. When I was in charge of project management at Loma Linda, we were working on the proton accelerator. The proton accelerator is this thing. I don't know if I defined it, told you what it is. It has this big 30-foot ring. They spin electrons inside this thing, and then they shoot them down a vacuum tube into rooms, and they treat cancer or other bad things inside your body. They shoot it inside your body. Proton therapies, particle physics. These guys are experts in that. I sat and talked to some of these guys, and based on my limited my basic math kind of stuff, I could understand what they were talking about, but these guys were experts. And so a lot of the stuff, some of the stuff that they do in talking about and try to explain to us how particle theory works, they are experts. That's what a defined expert in that area. Talk about really, these guys man, they're really smart dudes to be able to handle that kind of stuff. Particle physics is very, very, very deep, hard math. But that's what an expert would do. And one of the things we want to do with an expert series is we got these people and they're very limited subset of humanity that know and can understand that kind of stuff. So what we want to do with an expert system is how do we go and get that information and put that into a computer and use that for things like AI and thinking. And I would almost, and the thing that I think is going to be interesting to see is, because those people, they're very smart people to start with. But then if there's nobody else, if they're not interacting with somebody else, we put that into a computer. Are we no longer going to have experts in that area? Because people, I don't know, this is one of the great mysteries of the world to me. I think, are there going to no longer be experts in that area because we're going to have computers, we're going to rely on computers to do that? Could be. Is that, I don't know, any thoughts? Is that a good or a bad thing? I don't know. As long as we have that information and we can still get it from a computer, I'm not so sure it's detrimental that people can't do it, right? I don't know. Right? I don't know. Anybody thoughts? I don't know. As a parallel to that, I remember back in the day, when my early days in math, we didn't have real computers to do things, but we did everything on calculators. I had all my math classes. We had these scientific calculators, and we'd have to do things. And I remember, now nobody uses calculators like they used to, scientific calculators anymore, right? And there's a part of me that says, darn it, we had to learn on that. And here's the old man speaking. We had to learn it like that. And now, these kids, they don't understand why they don't. But do you need to? Yeah, maybe not. Maybe not. If you have the information, you can Google it or get the information quickly. Do we need to? I would say in some cases, no. Here's my soapbox speech. I do think we need to understand, and some of the stuff like that, with using calculators and manually calculating things, that's critical thinking skills. It teaches you how I got some information, I got to get to here. How do I get there? I think that's what we're losing is we're not getting the critical thinking. Okay, I'm here at A and I got to get to C or D. How do I get there? And some people, because they were not really forcing critical thinking anymore, we just look things up. I think we're losing more and more people can't think critically. And that's why when I fix things, I'm very good at, this is the problem. It's problem solving, critical thinking kind of stuff. Back off my soapbox. I'll get back. Sorry. Back to our regularly scheduled program. Because expert systems can integrate and manipulate response data, they perform better. Because if we can take that knowledge from an expert and put it into a computer, and then we can take all these other sources, integrate them together. Now we're taking that expert, which, like I said, these particle physicists, really smart guys, but they're still going to only be limited to the knowledge they have obtained in that. Whereas we can continually refine those algorithms, make them smarter and smarter and smarter, and do things perhaps beyond what they would, and in any individual or maybe a small group of individuals can do. So that's why it's very valuable to have these expert systems. But expert systems do present problems. The next slide, of course, lead into the next. Some of the things we have to be considered. Transferring that knowledge from a person, from that person to the system can be very difficult, and for multiple reasons beyond kind of what this said. So and I talked about that. I had that little cartoon slide about interviewing somebody and finding things out. Can you imagine? So if I had, I've actually, like I said, I've sat down and I've talked to these particle physicists. And they can explain things to me, and with my limited math knowledge, I kind of get it. Now, let's say I didn't have to do this, but let's say my job was to translate that into expert knowledge and store that in there. You have to have a much deeper knowledge of how to do that. I have to be much better at asking questions. Well, what do you mean by, I don't know, this, boson theory of how this, these electrons interact with each other, and I can only go so far. I'm not smart enough. So you have that translation from one to the other. And unfortunately, they're probably, and this has been my experience, the really, really smart people like that, they tend to be, they can, they'll just say, well, it's just obvious, the little thing. They're not good at explaining exactly something is so intuitive to them. They just think, well, don't you get it? Don't you get it? I had a math teacher once that said that. I don't know, here, I'm digressing too many times. I had a math teacher, one of the best math teachers I've ever had. And he explained things in really, really good detail. And he would get up there and break things down better than any math teacher I've ever had. And one of the things he said, and I thought this is so profound, it stuck with me the rest of my life, is one of the reasons, he goes, you guys might think I'm smart and I'm really good at math. But he said, I am just one of the biggest knuckleheads in math. He said, because I don't get this stuff intuitively. I have got to sit and study and figure this out and really work hard to understand it. So when I'm up here teaching it, I teach it the way I had to really break it down and figure it out because I'm not that smart. And that kind of makes sense. That's why he was a good teacher, because he explained it because he had to figure it out himself. Whereas somebody who's really smart and just looks at, oh, it's obvious, and those people have trouble explaining stuff because, what are you, dumb? You don't understand it? It's intuitive. So that's why I think some of the people, it's better. The people that are not quite so smart, but work harder to figure it out, make perhaps better teachers. Another one of my soapbox lectures. Last lecture, maybe I'm giving my I don't know why. I had no intent of doing those kinds of things. All right, so moving right along, getting back in. Even the domain experts can explain their process. Automating that process may not be possible. So with that, and this, so one, it's hard to get it out from them. I may not be smart enough to translate it. And then now that I understand it, oh my gosh, we've got all this new technology, we got the chipsets, we got everything to do it, but it's still just the technology in AI may not be there. So we may not be able to implement it yet. But that's not to say we're going to give up. We're going to keep trying. And that's one thing I think is really good. Just because technology fails the first time, don't give up on it. Just, this stuff doesn't work with the crap. Now get rid of it. This technology stuff. A lot of times what we do is we say, okay, that we tried, we failed, but let's try to refine it, or let's shelf it for now. And maybe 5 years from now, if the technology advances, then we'll use it and make it pop, and we'll find it viable at that point. In some context, there is a potential liability in the use of expert systems. In some areas, we're starting to use things. Let's say in that area of using the proton theory, these particle physicist information using the proton theory. Let's say we say, a couple of these guys, they get old, they pass away, or they retire, or whatever, we don't have access. And now we're fully relying on these expert systems. And, I feel like, we implemented it pretty well. However, some weird case, you have a new person comes in and they have some weird volume inside them, that we're trying to treat, something, that we just hadn't seen before. And we're using this expert system to figure out how to deal with that issue. What if it doesn't work right? And we end up killing the guy, killing a patient or something because of that. So there is liabilities. And so that one of the things we're always looking at with AI is, can we fully rely on it? And is it totally trustworthy? I think I've mentioned, I have a daughter that's a doctor, and she says she does look sometimes, she says she'll take symptoms of somebody and use like ChatGPT. I don't know if she uses ChatGPT or some other AI engine, and they'll look it up and see. And she said, sometimes it's just, she goes, I don't think that's right. She said, I don't trust that. So you've got to still, at this point, we're much better. It's helping a lot, but we still have to think about it a little bit. I have a nephew too. I guess I'm fortunate. My nephew's an attorney. He uses, I know he uses ChatGPT to do legal research for a legal brief that he's writing. And he says it works really good. He doesn't have to do as much research, but he says he'll put out a query, and the query comes back and gives him all kinds of legal briefs from, back prior cases and stuff. But he says, sometimes I'll read through them and he's like, that's not even relevant to what I'm looking at. So we still have to watch and look for that, because if he just blindly used everything, it could be problematic and not correct.
Even made up cases for it.
Oh, yeah. Absolutely. And I gotta say, I was talking earlier, we got into a conversation about my graduate class. My graduate class, I do all essay questions. And I explicitly, though, if you take me for a graduate class, you're gonna see essay questions. And I explicitly say, do not use an AI engine in this, because I'm looking for it, and I ran through a thing that I have that will kind of tell me, to be honest, if you used AI or not. But there are some that the writing's actually pretty good. It doesn't feel like AI to me. But then as I'm reading through it, there's stuff that's like way left field, and I'm like, okay, where did this come from? And so I'm just saying, buyer beware at this point with AI especially. Don't just wholesale use things, because it may or may not, because I've seen stuff, I can't think of an example off the bat, but I've seen stuff that's just not, it's like, this is way off, this guy went way off topic on this answer. It's not even close. It's probably AI generated. So be careful. We're not quite there yet. All right, so let's now move forward to machine learning, and another video. You haven't seen enough videos today, have you? I got a handful. This one I have a lot. There's just so
Step
much
into
out there
Wix
right now
Studio,
with AI.
where
stuff.
creative freedom meets absolute efficiency. Intelligent design scaled by default, and even advanced layout.
Machine learning. Teach a computer how to perform a task without explicitly programming it to perform said task. Instead, feed data into an algorithm to gradually improve outcomes with experience, similar to how organic life learns. The term was coined in 1959 by Arthur Samuel at IBM, who was developing artificial intelligence that could play checkers. Half a century later, and predictive models are embedded in many of the products we use every day, which perform two fundamental jobs. One is to classify data, like is there another car on the road, or does this patient have cancer? The other is to make predictions about future outcomes, like will the stock go up, or which YouTube video do you want to watch next? The first step in the process is to acquire and clean up data. Lots and lots of data. The better the data represents the problem, the better the results. Garbage in, garbage out. The data needs to have some kind of signal to be valuable to the algorithm for making predictions. And data scientists perform a job called feature engineering to transform raw data into features that better represent the underlying problem. The next step is to separate the data into a training set and testing set. The training data is fed into an algorithm to build a model, then the testing data is used to validate the accuracy or error of the model. The next step is to choose an algorithm, which might be a simple statistical model like linear or logistic regression, or a decision tree that assigns different weights to features in the data. Or you might get fancy with a convolutional neural network, which is an algorithm that also assigns weights to features, but also takes the input data and creates additional features automatically. And that's extremely useful for datasets that contain things like images or natural language, where manual feature engineering is virtually impossible. Every one of these algorithms learns to get better by comparing its predictions to an error function. If it's a classification problem, like is this animal a cat or a dog, the error function might be accuracy. If it's a regression problem, like how much will a loaf of bread cost next year, then it might be mean absolute error. Python is the language of choice among data scientists, but R and Julia are also popular options, and there are many.
You don't need to know the languages that are used for these things. All right, let's jump back over there, back over the chart. So basically machine learning are systems that are designed to, expert systems we're taking expert, we're trying to figure out how to make that system work like an expert. Machine learning, though, is programming the machine to continually learn, just like we do, when you're a kid, when you're exposed to certain different things and you learn things based on experience or seeing different situations as they come up. So that's what machine learning is trying to do, based on the ability to learn and improve the thinking. So that, and it kind of showed different things. Some of the stuff like autonomous driving vehicles. A lot of AI goes into that, machine learning as we're driving, and some of the test vehicles that they would go, as you're driving down the road, there's people putting inputs and telling it, okay, we're driving down the road, and you have to make judgments based on certain things. And you've probably heard some of the classic learning kind of things that has to do as you're driving down the street. If the car is driving and now it has to make a decision, if it's fully autonomous, if it crashes into the car in front of it versus swerving or doing some evasive maneuver, but then there's like people standing on the side. That's a machine learning kind of thing. Which do you do? If you are going to either hit the car in front of you or hit a group of people standing on the side, which would you prefer? Well, neither one's a good solution, right? But if something's gonna happen, the better solution probably is to hit the car in front of you, right? You might hurt the people in front of you, but people standing on the side, you're gonna probably kill them easily. So, but it's that kind of learning kind of stuff is what goes into autonomous driving. And plus, things like, well, if you're swerving, or is this kind of a line? Is that a real line, or is that just something in the road? So that kind of learning is what goes into things like autonomous driving. And that's what the last bullet just talks about. The difference between expert is trying to understand what experts do, and then machine learning is trying to continually make the computer smarter and smarter and smarter. And that's not to say that they're not linked, because in some expert systems, that's what they do. They take that expert information, and then we try to make it smarter by incorporating machine learning kind of techniques. And the next chart talks about some of these different types of machine learning. You go over there. Another video, of course.
Get ready with me to type an essay. First, I'm just getting some water to refresh myself and a little snack.
Hello. In this video, we'll provide some basics on supervised and unsupervised learning. An easy way to begin grasping the concept of supervised learning is by looking directly at the words that make it up. Supervise means to observe and direct the execution of a task, project, or activity. Obviously, we're not going to be supervising a person. Instead, we'll be supervising a machine learning model that might be able to produce classification regions like we see here. So how do we supervise a machine learning model? We do this by teaching the model. That is, we load the model with knowledge so that we can have it predict future instances. But this leads to the next question, which is, how exactly do we teach a model? We teach the model by training it with some data from a labeled data set. It's important to note that the data is labeled. And what does a labeled data set look like? Well, it can look something like this. This example is just taken from the IRIS dataset, which is a famous dataset used for machine learning. Let's start by classifying some components of this table. The names up here, which are called sepal length, sepal width, petal length, petal width, and species, are called the attributes. The columns are called features, which include the data. If you look at a single data point on a plot, it'll have all of these attributes. That would make a row on this chart or an observation. Looking directly at the value of data, you can have two kinds. The first is numerical. When dealing with machine learning, the most commonly used data is numeric. The second is categorical. That is, it's non-numeric, because it contains characters rather than numbers. In this case, it's categorical because this dataset is made for classification. Usually, a dataset like this will be put into a .csv file, or comma-separated value file. This file separates observations by new lines and attributes by commas, hence comma-separated. There are two types of supervised learning, classification and regression. Since we know the meaning of supervised learning, what do you think unsupervised learning means? Unsupervised learning is exactly as it sounds. We do not supervise the model, but we let the model work on its own to discover information that may not be visible to the human eye. Unsupervised learning uses machine learning algorithms that draw conclusions on unlabeled data. Unsupervised learning has more difficult algorithms than supervised learning, since we know little to no information about the data or the outcomes that are to be expected. With unsupervised learning, we're looking to find things such as groups or clusters perform, density estimation, and dimensionality reduction. In supervised learning, however, we know what kind of data we're dealing with, since it is labeled data. In comparison to supervised learning, unsupervised learning has fewer tests and fewer models that can be used in order to ensure the outcome of the model is accurate. As such, Unsupervised learning creates a less controllable environment as the machine is creating outcomes for us. Now, let's investigate a machine learning algorithm. Here we can see the output of an algorithm applied to examining poisonous mushrooms. As you can see, it tells us if a mushroom is poisonous or edible, depending on its features. So without looking at the data itself, do you think this is a supervised or unsupervised machine learning problem? The answer is supervised machine learning, as this is an example of classification. That is, it classifies mushrooms into two different labels, poisonous or edible. Specifically, it does so using a classification tree algorithm. The biggest difference between supervised and unsupervised learning is that supervised learning deals with labeled data, while unsupervised learning deals with unlabeled data. In supervised learning, we have machine learning algorithms for classification and regression. Classification is the organization of labeled data. Regression is the prediction of trends in labeled data to determine future outcomes. While it's possible to classify data using regression, covering that now is out of scope for this course. In unsupervised learning, we have clustering. Clustering is the analysis of patterns and groupings of unlabeled data. Thanks for watching.
If you're a teenage girl living almost any...
All right, close a couple of these guys. All right, so going back over here. So basically supervised versus unsupervised. Supervised, like you said, it's labeled, it's understood. I would say generally it's understood. We can actually put classifications on there. So that's why, these things called labels are created for them, and they create different characteristics about them. And in a supervised environment, you start looking and it looks at patterns, and usually they're checking it. Yeah, that makes sense. And so we have, and it is kind of watched by a person. Whereas unsupervised, the big differentiation is it's usually not as easily characterized. We can't put labels on it. It's random kind of stuff. And as you say, they're random. And as we've talked, I've talked before, some of the stuff that's just, it's hard to characterize, hard to understand it. You just put all this stuff into a blob, and there's harder, more complex kind of algorithms that look at it and try to say, oh, okay, well, let's try to make sense out of all these things that are very disparate and not really similar. And let's let the computer try to find patterns, trends, relationships amongst that data to come up with solutions, come up with answers for it. So supervised, much better understood. Kind of problems usually can be classified and put into labels versus unsupervised, just random stuff. And you just let the computer go nuts trying to figure out based on no real criteria. And then there's semi-supervised. Obviously, there are things in the middle. There are situations where the information, we kind of understand it, or we understand parts of it, but there are parts we don't. So what we do is we characterize what we know, and then we say, okay, we're gonna run that in a supervised mode. But then we're also gonna throw it at an unsupervised kind of environment and let the computer try to figure out additional things beyond what we were able to discover from the supervised mode. So it's kind of in both. And I also have a video on reinforcement. But anyway, let's talk about reinforcement. These are all real.
Hey, Charles, this is when we get to talk about reinforcement learning.
Good.
Hi, Michael. This is when I get to hear about reinforcement learning.
Wow, I'm glad we're on the same page. So,
are we on the same page? Is this all of reinforcement learning, or is it just the reinforcement learning basics?
We're going to start with the basics.
Okay, I can't wait to hear what that is.
So the first concept to try to understand when you're doing reinforcement learning is that a lot of it takes place as a conversation between an agent and an environment.
Okay, so like right now, you're the agent and I'm the environment?
Actually, I think I'm going to have you be the agent.
Okay.
And we'll just imagine some kind of, I don't know, like a video game environment.
That seems reasonable. By the way, have you noticed I've lost weight?
Oh, good job. How did you do that?
Well, I got drawn as a stick figure.
That's fair. So here we are, the agent and the environment. And the conversation basically talks about what is going back and forth between the agent and the environment. So the environment is going to reveal itself to you, to the agent, in the form of states, S. You then get to have some influence on the environment by taking actions, A, and then you also receive back
before the next state, some kind of reward for the most recent state action combination.
Okay, fair enough.
So this is the same kind of elements that we have in an MDP. But the important thing is that instead of just being given an MDP as some kind of a graph structure and then we get to compute on it, really the computation is happening inside the head of the agent, and the information about the environment is really only available through the course of this interaction. So does that make some sense?
It does make some sense, but I guess, how is that any different from the NDP?
Well, it is. It's the same story as how a policy interacts with an MDP, right? Where this is playing the role of the MDP, and this is playing the role of the policy pi. But now, again, the computational aspect of the system here, the agent doesn't know the environment. It's not living inside the agent's head. Instead, the agent is just experiencing the environment by interacting with it. It could then, if it so chose, build some kind of a model of the environment in its head and then think about that. But what's in the agent's head and what's in the environment are two different things in this setup.
Okay, fair enough. I get that.
So maybe I can make this a little bit clearer. So let's actually put you in this environment. What do you say?
Okay, metaphorically?
No, let's just do it.
Sure.
I like that one. Go back and look, find a better one, reinforcement. Let me talk a little bit more about reinforcement. Reinforcement basically
Most
is
people
kind of how
have
we
no
learn.
clue that in 2023, the best way to make money on Amazon is not with physical.
Not the watch card commercials.
Yeah.
Sorry, go back over here, sorry. All right, so reinforcement is more, I think of that along the lines of how we learn. When you're a little kid, and you're learning, you have different experiences and you get reinforcement, you get information back. Like you say something to your parents and your parents correct you. They say, no, that's not quite right. So you get reinforcement or you get corrected on how it is. And that reinforcement, usually positive, depending on how you do it, there's all kinds of, I'm not getting into the psychology of it, positive reinforcement versus negative. Every time you say that word wrong, I'm going to spank you and, I'm going to, positive reinforcement, usually works a lot better. So it's that basic same thing. You do something, you try it, and oh, no, that's not right. So that's what in machine learning, one of the things they do is we, especially more probably in supervised mode, we let the computer run, try to figure something out, and then somebody observes and says, yes, that's right, and tells the system, yep, that's a good one, keep it. Or no, bad, kick that out. So the reinforcement says, what are the things you're doing right and what are they doing wrong? And that's kind of how we learn. And I think of language. I'm actually, because I got nothing better to do, I'm crazy busy all the time, but I'm just learning. I've decided, anybody familiar with Duolingo? Anybody Duolingo?
Yeah.
Duolingo, anybody else do it? I'm learning Spanish right now. My wife speaks Spanish. My daughters speak, and I'm learning. I've been doing it for not even a year yet. Please don't speak Spanish to me because I'm horrible. I can understand a lot of it, but I'm like, I'm just too timid to speak in Spanish. I brutally hammer it. So anyway, but I'm learning. Duolingo is exactly that. Try to, do it. Whoops, nope, you're wrong. And so that's reinforcement kind of learning. I don't know why. Now that you know that I'm learning Spanish, please speak Spanish to me. I'm terrible. All right, so one more, another video. I didn't realize I had this many. All right, deep learning.
Ever wondered how Google translates an entire web page to a different language in a matter of seconds? Or your phone gallery groups images based on their location? All of this is a product of deep learning. But what exactly is deep learning? Deep learning is a subset of machine learning, which in turn is a subset of artificial intelligence. Artificial intelligence is a technique that enables a machine to mimic human behavior. Machine learning is a technique to achieve AI through algorithms trained with data. And finally, deep learning is a type of machine learning inspired by the structure of the human brain. In terms of deep learning, this structure is called an artificial neural network. Let's understand deep learning better and how it's different from machine learning. Say we create a machine that could differentiate between tomatoes and cherries. If done using machine learning, we'd have to tell the machine the features based on which the two can be differentiated. These features could be the size and the type of stem on them. With deep learning, on the other hand, the features are picked out by the neural network without human intervention. Of course, that kind of independence comes at the cost of having a much higher volume of data to train our machine. Now, let's dive into the working of neural networks. Here, we have 3 students. Each of them write down the digit 9 on a piece of paper. Notably, they don't all write it identically. The human brain can easily recognize the digits. But what if a computer had to recognize them? That's where deep learning comes in. Here's a neural network trained to identify handwritten digits. Each number is present as an image of 28 × 28 pixels. Now, that amounts to a total of 784 pixels. Neurons, the core entity of a neural network, is where the information processing takes place. Each of the 784 pixels is fed to a neuron in the first layer of our neural network. This forms the input layer. On the other end, we have the output layer, with each neuron representing a digit with the hidden layers existing between them. The information is transferred from one layer to another over connecting channels. Each of these has a value attached to it, and hence is called a weighted channel. All neurons have a unique number associated with it called bias. This bias is added to the weighted sum of inputs reaching the neuron, which is then applied to a function known as the activation function. The result of the activation function determines if the neuron gets activated. Every activated neuron passes on information to the following layers. This continues up till the second last layer. The one neuron activated in the output layer corresponds to the input digit. The weights and bias are continuously adjusted to produce a well-trained network. So, where is deep learning applied? In customer support. When most people converse with customer support agents, the conversation seems so real. They don't even realize that it's actually a bot on the other side.
Yeah, I do.
In medical care, neural networks detect cancer cells and analyze MRI images to give detailed results. Self-driving cars. What seemed like science fiction is now a reality. Apple, Tesla, and Nissan are only a few of the companies working on self-driving cars. So, deep learning has a vast scope, but it too faces some limitations. The first, as we discussed earlier, is data. While deep learning is the most efficient way to deal with unstructured data, a neural network requires a massive volume of data to train. Let's assume we always have access to the necessary amount of data. Processing this is not within the capability of every machine. And that brings us to our second limitation: computational power. Training a neural network requires graphical processing units, which have thousands of cores as compared to CPUs. And GPUs are, of course, more expensive. And finally, we come down to training time. Deep neural networks take hours or even months to train. The time increases with the amount of data and number of layers in the network. So, here's a short quiz for you. Arrange the following statements in order to describe the working of a neural network. A. The bias is added. B. The weighted sum of the inputs is calculated. C. Specific neuron is activated. D. The result is fed to an activation function. Leave your answers in the comments section below. 3 of you stand a chance to win Amazon vouchers. So hurry! Some of the popular deep learning frameworks include TensorFlow, PyTorch.
I do the commercials from here, so I'm gonna stop there. So deep learning, that's a quick explanation of deep learning. And that whole concept of neural networks, I'm gonna kind of go into that. Actually, I'm probably gonna go into the next chart, types of neural networks as well. Just fundamentally kind of to reiterate or kind of maybe explain better that whole concept. He went through neural networks, and I don't know if it's real well. The concept of a neural network is the kind of the prevailing thought of how the brain works. We see a lot of things going on, and because of that learning that we've done over the years, we pick up things and we see them over and over, and that reinforcement tells us different things. Well, using that 9 example, how we had a 1 9 that was like kind of more solid, then it was thinner line, then the last one, it was kind of curved. It almost could look like a G, right? Well, over time, we learn, our brain, we perceive, and we see lots of different 9s, and we see different writing, and our brain makes associations and says, the neurons in there say, okay, I've seen this before, and because, maybe that reinforcement or for whatever reason, This one, like that last one, I could say, that kind of looks like a G, but your brain knows that, maybe where it's located on, relative to the other letters, or maybe just based on, it was kind of elongated a little bit. Your brain says, okay, in my understanding of this, it's more likely to be a 9 than it is a G. And that's that matrix of things. I've seen a bunch of different patterns that first row of neurons are in our brain somewhere. We have these neurons that say, okay, this is what I believe it to be based on my experience or whatever, all the, different things I've seen. And so then your brain makes a decision very, very quickly that this is that's a 9, it's not a G. In fact, it could be a G, but based on, there's some error factor in there, but that's how the brain works. And that's what a neural network is trying to do, emulate that same way our brain works and create those same kind of experiences of the neurons that are in our brain and come up with conclusions based on that thought. And there's all kinds of this is just examples of different things that use neural networks, speech recognition, because we listen and we hear speech. I've heard, that we all, hopefully my English is fairly straightforward and easy to understand. But, there's different people from, even in the United States, have different accents, and we hear different people from Texas, from the East Coast. I used to travel to Boston a lot, man. They talk weird English, and and then you go to the UK, it's very, different words and stuff, but you can still understand it, right? So you learn different types of patterns, images, drug, and so we learn different images. I can look at an image like they were showing on the one earlier. Is this a dog or a cat? And they had that weird kind of. It was actually looked kind of like a. I think it was like a lion with a. I don't know. Was it a lion or a tiger? I don't know. With what? The tiger with a dog's face, you're like, what is that? So we can recognize things or not, and our brain can kind of sort it out. Drug discovery and toxicology, trying to figure out, taking in all kinds of information about different things, how they affect the body. This is actually, to me, a very interesting world. I think AI could have a big effect on that. I know I have friends. I have a couple doctor friends, as well as I have my daughter who's a doctor. The world of medicine, still to a large degree, I don't know if this is shocking news to anybody. It's very much based on pattern response. You come in, you tell me you have these characteristics. You have, I have runny nose like this, and they say, okay, based on that, I know that I've given this medicine in the past, or somebody's told me this one solves your problem. And so take this and hopefully it fixes it. It's really, in a lot of cases, not a science. I don't know if we always think that medicine is a science. No, did they run any tests to find out exactly what's going on inside your body? No, they just know, based on this information that you give me, I'm going to give you this, and it'll probably 90% of the time or 75% of the time, some percentage of the time, fix the problem. And do you know if the problem really got fixed or it just ran its course and went away? Did the medicine do it or not? Oh, who knows? And that's what that's the history of drugs and toxicology. I think over time, we're going to get smarter and understand things better, and it's going to become more refined. We're not going to be just chemically treating things. Just take this. It should fix it or not. So anyway, and autonomous vehicles, I've talked about autonomous vehicles. I think, they definitely are learning more and more and getting better at these kind of things. And the next chart, now we're actually getting a little deeper into some of these types of neural networks.
It's training a computer to learn like a human. A neural network is a type of deep learning, falling under the category of AI. It's a system of hardware and/or software designed to mimic how neurons in the human brain work. Stick around to learn how it works and why it's useful, but understand there are some limitations. Click the link above or in the description below to read up on neural networking challenges in the age of high data demands. A neural network involves a large number of processors operating in tiers. The first tier receives the raw input information, and each following tier receives the output from the tier that preceded it. Every processing node among all tiers has its own small sphere of knowledge that it applies to the input information. The last tier provides the final output. That's how it works. But how does it learn in order to provide an output? Typically, a neural network is fed huge amounts of data on the topic it will be used for. It's trained by providing input and telling the network what the output should be. Rules are also put in place to help the network learn. For example, a facial recognition system may be taught to recognize a mustache on a face. During training, the network will be fed pictures of people with and without mustaches, and telling it which photos do, in fact, have a mustache. It might also be instructed mustaches are below the nose and above the mouth. Rules like this can make the training faster and the end model more powerful. Neural networks are utilized by a wide variety of industries. Some notable applications of neural networking include speech-to-text transcription, handwriting recognition, weather prediction, facial recognition, chatbots, stock market prediction, delivery route planning and optimization, and so much more. What are some other applications of neural networking? Share your thoughts in the comments below and be sure to hit that like button.
A little bit more on neural network. Trying to think if I'm going to use that one in the future. I may cut that one out. So I think I explained it enough. All right, so so different types. So what are some of the different types of neural networks that they have? The first one up there is recurrent neural network. And a recurrent one usually is something that is very well known, understood, patterns of things, like the example he kind of gave. He used the example of people with mustaches and those without. That is something you can program a neural network fairly easy because there's a pattern. You either have one or you don't. Or you have certain characteristics, very set patterns of things that are well understood, kind of stuff. Like speech recognition, once again, there's certain words, even though they're said slightly different, you can understand that, it sounds enough like this, that it is something we can say, yeah, that is understood. So it recurs in life, we see it often, and then the neural network says, this is highly likely what it is, so it understands it. Then you have convolutional neural networks are things, and it's usually associated more with graphical kind of things, whereas it can look at an image and say, oh, okay, this, I understand what a line is, I understand what curves are, I understand the different geometric shapes, and it'll say, okay, I'll take that information and store and take that and put it into some kind of context, and then say, okay, I can understand color too, I can understand all the different shades of color, so it can start analyzing different imaging. So convolutional is kind of looking at things that are more graphic or picture kind of related, image kind of stuff. And then the last type of a neural network that is usually looked at, and the generative adversarial, and the kind of adversarial is probably the word. Some of the times, one of the things we want to do is you take two different neural networks that are hopefully not programmed by the same thing, but they work slightly different, and you have them, each one of them kind of compete, and you'll feed different information. You might feed in recurrent kind of stuff. We have this recurrent information, we'll feed stuff into there, and then we'll feed it into the other one, and we'll have them both, I guess for lack of better terms, compete with each other and say, oh, okay, this one, and then I'll look at it and say, yeah, that one came up with a better answer than that one. And so you have them kind of compete, and then by that process, they each optimize on each other based on the answer the other guy got, and it creates, that once again, it's kind of like the brain works. I saw these things, I didn't believe that, I do, but, and you kind of create a new reality based on some competing information that goes on. So that's what the adversarial or the generative adversarial network works like. All right, so this last chart is I think it's just some examples of artificial intelligence applications, different things we see in there. Maybe I'll show, I don't know if I'll show all these. Some of these are kind of interesting. Some of these, I think one of these is kind of freaky. I'm not really going to do it. Little short videos. Oh, well, I guess we won't show that one. Isn't available anymore. Man, I just added some of these like last semester. That one disappeared quick, huh? Let's see I think this is the one that I think is kind of cool.
What is natural language processing? Imagine you're at the hairdresser. The receptionist tells you the stylist is free. But what does that mean? That the haircut doesn't cost anything? That the stylist has been released from prison? Of course not. It means the stylist is ready for your haircut. You know that because you have context. Computers are programmed to identify written and spoken words, but to really communicate with people, they need to understand context. That's where natural language processing, or NLP, comes in. Computers use NLP to look beyond individual words or phrases and understand the context they're being delivered in, often enough to communicate with virtually anyone in real time. Natural language processing lets virtual assistants like Siri and Alexa understand that when you ask them to play some rock, you're not asking Siri to pick up a guitar or start banging stones together, but to play some tunes. We hope this video on natural language processing makes sense. What is natural language?
So using AI and for natural language processing, and that is there's kind of I don't know, maybe subtle, but there is an important differentiation in there. Some of the older AI kind of stuff didn't take things into context. Context is very important, and that's one of the things I noticed. It's kind of interesting for me when I've kind of dabbled now with a little bit with ChatGPT and some AI kind of things. The historical ones, you would type something into it, and it would give you a very like he was saying. If I said they use the example something of a rock. Well, a computer, if it doesn't put it into context, a rock could be a physical rock to throw it at it. Whereas they're showing here, the person really intended rock music. So having no context of what the person intends, it doesn't help you much. But that's what some of the newer AI functions are doing. ChatGPT, it'll you type in a question. Has everybody tried ChatGPT? If you haven't, do it. It's kind of fun. You type in a question, and it'll answer the question. And then if you type a follow-on question, it'll understand, okay, the prior question you asked about this, it'll use that context and further delve into it more. So it's using context, and the more context you give it, the more refined or better answers you get. I wouldn't say it's perfect, but it's getting better. And that's one of the things that artificial intelligence is doing more and more, is using context. Whereas some of the old original stuff, 20 years ago, horrible at context kind of looking at. Speech recognition, intelligent agents, last one. It's the last chart, last one. Let's look at it.
The all-new Pizza Hut $7 deal lovers menu, because it's only a deal if you love it.
Are you struggling in your calculus class?
No.
Do you have a hard time understanding your instructor?
No.
Do you wish there was a
Now, robotics are driven by a form of artificial intelligence, multiple forms of artificial intelligence. And we could have spent this entire time just talking about the impact of AI on your businesses in the near future. But let me summarize some of the key points. Data comes in through your business infrastructure, and the amount of that data is increasing exponentially, especially as a result of the Internet of Things. But think of all the unstructured data that comes in through the internet, the World Wide Web, social media, Twitter, and so forth, Facebook, all that stuff, information, comments about your products, how they're being used, what people like, what people don't like. And using tools like natural language processing and voice recognition, that data can be converted into digital format where it's not already digital, such as comes from the Internet of Things. And then using that input, tools like associative memory for pattern recognition and machine learning can allow intelligent agents to think, decide, and act in ways highly analogous to how human experts deal with the same problems in terms of solving business problems and continuously improving those processes by feeding the results of those efforts back into the decision-making process. And intelligent agents, one of the challenges each of us have in our organizations is the Pareto principle when it comes to the effectiveness of our people. Typically, the 20% of your best people produce 80% of the results, whether it's in sales, whether it's in operations, in production, in credit management, or procurement, or whatever you have. Wouldn't it be great if you could get all 100% of your people performing as well as the 20% that are the best? If you could only take one of those very best people and have them look over the shoulder of the people who are less knowledgeable and experienced and coach them through every day. Of course, you can't afford to take those people off the job, but with intelligent agent technology, you can increase the capabilities of those people. Perhaps they won't immediately match the performance level of the very best, but instead of them performing at 40 or 50% of that level, if you can get them to performing at 85 or 90%, think how much more productive that's going to make those people. Furthermore, your very best people can have their productivity significantly increased because they spend too much time now doing routine, low-level number crunching and analytics that can be done better, more cost-effectively by intelligent agents, allowing them to focus their time and attention on those things that need their judgment and experience and creativity to allow them to do a still better job too. So intelligent agents are going to have a huge role for us moving forward.
I don't know how easy that was to understand, but looks a little rougher. Intelligent agents talking about, having things, and he's talking from an organizational standpoint, helping people think better. And he talked about the 80-20 rule. Everybody here familiar with the 80-20 rule? 80-20 rule is 20% of your people do 80% of your work, and vice versa, 80% of the people, And so it's, you always want to focus on, 80% of the people do 20% of the work and 20% of the people do 80% of the work. So you always want to look at and try to how to increase that and get more people to do more stuff. And actually, the first time I heard it was 80% of your employees will cause 20% of your problems, and 20% of your employees will cause 80% of your problems. So it kind of talks to a little bit, from an organizational behavior kind of thing. Those 20% are the ones that you're gonna spend a bad employee you spend a lot of time with. If any of you supervise, you'll fully understand that. You have that one employee that just seems to be toxic, causes all kinds of trouble, and you spend so much time dealing with that issue. Very much true. Anyway, intelligent agents trying to look for ways to do things smarter within the organization, using intelligence to process things faster. That's the end of the chapter 14. Make sure you do the quiz this week. There will be no class on Thursday. Like I said, I am not going to have a recording on it because I have finished chapter 14. That's the end of what I'm going to cover for the course. Groups 5 and 6, make sure you upload your video, and I think that's it. Yeah.
So just to be clear, you said that next week the finals on Thursday, not Tuesday.
Thursday at 9 o'clock, correct.
Not be coming to class Tuesday and
Correct.
Thursday.
Just no class on Tuesday next week. And I'll make sure I put that piece in the announcement too.
Okay.
All right. All right. Thank you for asking. I appreciate it. Stop the share. I do have a question. Anybody? I've started to incorporate, like in this one, more videos, and then I try to elaborate the videos. Is that, do you think that helps?
That does help. Yeah,
It's better learning that way.
Yeah.
Because this is what sometimes, over the years, I know that I used to just straight lecture the whole time and try to get discussions going. And I feel like sometimes I get tired of hearing me talk. And so I think having a video, and then, they talk about show graphics, and then I can elaborate on the things I think that you need that might not be clear, or
especially since you mostly do short ones, like 1 to 3 minute ones. I think those are really helpful.
Yeah, 10-minute videos, and then
yeah.
So it is helpful.
If they're too technical, then that's where you kind of get lost. But they've been pretty good at breaking down.
Yeah, okay, good.
It breaks up the monotony of a lecture.
Oh, yeah, I appreciate it. Yeah, and that's although I'm probably not going to teach much longer, I do like to try to look for new, like we were actually, Lauren, right? We were talking about this at the beginning. I wasn't sure if I get your name.
Yes.
It's all about effective learning. Are people actually learning stuff? I think it's AI. And I continually think about that. And we were talking about earlier. I think, now in this generation and the way we have technology, I'm not sure we're using, I think before you got here, maybe, I'm not sure we're using technology to actually learn. And in the discussion we were having is a lot of instructors, like in a online course, they just overwhelm you with busy work that doesn't really teach you things. And that's why I continually try to think of, okay, how can I make this that they actually effectively learn more than just throw them in, hey, go read this, write 10 reports,
Keeping it short and concise, so really talking about what really matters is best, because everyone has such a short attention span.
Yeah, especially now in today's society, that's more the case.
If I'm gonna take the test on Tuesday, I'm gonna email you.
No, just show up that day and then remind me. Anybody that comes, if you come that day, I may or may not say, wait, that guy's a 9 o'clock guy. I may or may not.
Okay.
There's sometimes I see, the person's on, but I probably just show up.
Okay.
Show up.
Thank you.
All right.
Next Thursday.
All right, next Thursday. Thanks. You have a good one.
Have a good day.
You too.